So now we're going to talk about how to determine continuity when you're given a formula, in particular, a piecewise formula. And again, this is continuity at a point, not of the entire function. Now, piecewise functions, let me draw a quick picture of a piecewise function. Piecewise functions are functions that are broken in to different pieces. So you might have a function that's first piece is a parabola, and then the second piece could be a line, or it could be any combination of different types of functions, but it's broken into pieces. So different parts of the domain have different pieces. Now, it is possible that you would have a function like this one with a parabola, and then the line actually meets up. I'll highlight it. Actually meets up, and actually those two pieces connect. Or it's also possible to have a piecewise function where the pieces do not connect. So maybe you do have a parabola again, and then maybe the line doesn't pick up until further down. So it's possible that the pieces could connect, or there could be a discontinuity right there where they join. So that's what we need to inspect here. We need to check on the continuity of the value of x where the rule changes. So we're really interested in what's happening in these points. Now you'll find those values of x's right here. So on number 3, I'm interested in what's happening to this function at x equals 1. On number 4, I'm interested what's happening to this function at x equals -2. So I'm interested in what is happening with this function at these particular points. Now, how do I check this? I'm going to check it with the definition of continuity. So here's a reminder. Let me grab my pencil again with that definition of continuity. At a point. Okay, so there are 3 conditions that have to be met. I'm going to do them in a little bit different order, but the first one is that the value at that x value has to exist. Has to exist. So first of all, you want to find f of that value, so f of 1, and figure out, does it exist? The second thing you're going to need to do is you're going to have to figure out, does the limit exist as x approaches that x value? So does that exist? Now, with piecewise functions, they're broken into 2 different pieces, and we are examining what's happening to x around that piece. So to check this second condition, we are going to have to check the left and right-hand limit. L and R stands for left and right. Check the left and right limit. Then that third condition is that the 2 above give you the same number. In other words, whenever you find f of c, you get the same thing that you get whenever you find the limit as x approaches c of the function. So those two, the 2 numbers that you get in 1 and 2 have to be the same. So let's try this out on example 3. So I need to figure out, does f of 1 exist? So condition 1, we need to figure out what f of 1 is. So I have this function right here. It tells me that I'll use the top formula whenever x is less than or equal to 1. And since I'm going to substitute in 1, I'm going to put 1 in for this x squared. So I'll have 1 squared minus 3, and 1 squared minus 3 is -2. Okay, so condition number 1 is met, check, because I got a value whenever I substituted in 1. I didn't get an undefined value. Second condition, now this is a piecewise function, and I do need to check the left and right hand limits first. So I'm going to find the limit as x approaches 1 from the left of f of x. And then I'm going to find the limit as x approaches 1 from the right of f of x. Okay, so to find the limit from the left, I'm going to use the formula that approaches 1 from the left, which is the top formula. That approaches 1 from the left because it says less than. And I can just substitute in the 1. So that would be 1 squared minus 3, which is -2. Then I want to check the limit as x approaches 1 from the right. So I'll use the formula that has x values that approach 1 from the right. 1 minus x. So 1 minus, substitute in 1, I get 0. Now, does the limit exist? Well, are these two the same? No, these are not the same. So since the limit from the left and the limit from the right are not the same number, then that tells me the limit as x approaches c of f of x does not exist. And since the limit does not exist, that implies that f of x is not continuous at x equals 1. So I've checked the first condition and it was satisfied. I checked the second condition, it was not satisfied. So since it wasn't satisfied, I can go ahead and stop. I don't even need to check the third condition. So if any one of these three conditions are violated, you can go ahead and stop and say this function is not continuous at 1. So for example 3, I only had to check the first two conditions. Now to make sure I have space, I'm going to scroll down and do example 5 now. This time I'm interested in seeing what's happening at -1. So first condition, find f of -1. So it looks like I'll use the top formula because it has that or equal to part, which is 3 to negative x. So 3 to the negative, and I'm going to substitute in -1 for x. 3 to the negative 1 is the same as 3 to the positive 1, and 3 to the positive 1 is 3. Well, I got a value, it's defined, so condition 1 is met. Condition number 2, let's work on finding the limit. Find the limit from the left and then the limit from the right. The limit as x approaches -1 from the left of f of x. I need to pick the formula that approaches 1 from the left. It's the top one because these x values are on the left side of -1. So I'll take 3 to the negative, substitute a -1 again, and you'll notice I'm doing the same thing. And you'll always do the same thing for one or two of the pieces of the function. So 3 to the positive 1, which is 3. Okay, now let's check the limit as x approaches 1 from the right of f of x. So this time I need to think about x values that approach -1 from the right. So that looks like it's the bottom formula. So I'm going to substitute 1 in for x right here. 1 over 1 plus 1, which is 1/2. And so I did get a number that exists, but are these two numbers the same? No, these are not the same. So that tells me that the limit as x approaches -1 of f of x, that writing looks weird. The limit as x approaches -1 of f of x does not exist. Does not exist, or D and E. And since the limit does not exist, that's going to imply that f of x is not continuous at x equals -1. Now I'm looking at this symbol right here, and I'm thinking you guys probably have a question about what I'm writing right there. So that is a symbol for that implies. And so that is it looks like an arrow, but it's got an extra line underneath. So whenever you draw an arrow with two lines, it means that implies. Just like, that's what I'm doing with that symbol there. It's hard to see whenever I'm handwriting on a slate here. Okay, now here's an example on Delta Math. Determine whether a function f of x is continuous at -6. So let's check. What is f of -6? F of -6, if I substitute it, looks like I need to substitute in the bottom equation, so or bottom formula, -12 plus 3 times -6. That's -12 minus 18, -30. Condition number 1, I got a value, that's met. Condition number 2, what is the limit? I need to check from the left and the right. So the limit as x approaches -6 from the left of f of x. I'm going to use the bottom formula this time because notice it says these are the values that approach x from -6 from the left. So that's going to be -12 plus 3 try that again, going too fast. Negative 12 plus 3 times negative 6, again, is negative 30. Now let's find the limit as x approaches negative 6 from the right of f of x. Let me erase what's going on here. Okay, so from the right, this tells me that these values of x are on the right side of negative 6. So I'll use this top formula and substitute in negative 6. 6 minus x squared, but instead of x squared, I'll put negative 6 in there. So that's how I have more space. 6 minus negative 6 squared is 36. And 6 minus 36 is negative 30. Oh, look, these are the same. So since those two are the same, then I can say that the general limit, or the limit as x approaches negative 6 from the left and right, is negative 30. Whew, now we can make it to condition 3. Condition 3, is this number the same as that number? Yes. So since f of negative 6 is equal to the limit as x approaches negative 6 of f of x, so we'd say since that is true, f of x is continuous at x equals negative 6.